as the title suggests, it basically makes use of the evaporation process of water vapor to provide the cooling effect. And this is a very different way to cool the air or cool the water as compared to what we have done in chapter 10, right? So this is a very interesting technique. This is something that's used very frequently, and I'm sure you have seen examples of it once I show the pictures. So it's something very interesting to learn about, and it's a very useful technique as we will learn more about it. So evaporative cooling is what's used in these desert air coolers, for example, or the air humidifiers or that you see in the Herman mosques, right? Both of these work on the principle of evaporative cooling, and this evaporative cooling is pretty effective in places with hot and dry climates, such as Riyadh, for example. So this plot right here shows you the relative humidity over the years, over the duration of a year for Riyadh, and in the summer, which is basically these ones right here, the relative humidity is pretty small. Okay, it's less than 20%. So let's have a look at how this entire process works, right? With the example of the air cooler. So in the air cooler, you have water, liquid water dropping from the top, right, and into a pad, and you have hot dry air entering the pad, and basically we have a fan that ensures the circulation of air. So it's basically pulling in the air. Okay, so now as the hot dry air comes into contact with this liquid droplets, some evaporation occurs. And now for the evaporation to occur, the latent heat of vaporization needs to be provided from somewhere. The HFG, the difference between HF and FG, needs to be provided from somewhere. And that basically comes from the dry air as well as the water that remains as liquid. So basically the temperature of these two things, the dry air as well as the water that remains as a liquid, goes down, thereby providing the heat input for the evaporation of some part of the liquid water. All right, and basically just through evaporation, right, the cooling effect is reached for both water and the liquid water. The liquid water and the air. And what you have is moist and cool air coming out from the other side of the cooler. Okay, so again, this is going to be very effective if you have hot and dry air. Dry is a key component because the lower the relative humidity, the higher or the easier will it be for air to accept more moisture content. And therefore, as I showed you here, in places like Riyadh, which are hot and dry, these kind of coolers make a lot more sense in summers. So if you recall to our discussion on what sort of relative humidity do we need for our comfort, we said we need relative humidity between 30 to 50%. So as you can see here, once you have hot dry air going through this evaporative air cooler, the air that comes out on the other side is going to be cooler and also more humid. So especially when you consider the inlet relative humidity to be 20%, we're going to increase that a bit, right? And that's like a win-win situation. You're achieving both aims. You're cooling the air and also humidifying it when necessary. Okay. Now, if you look at a psychrometric chart, this is how the process would look like. This is the inlet of hot dry air here, T1, and as it goes through the evaporator, evaporative pad, where it transfers, rejects some heat essentially to the water that gets evaporated. The moisture basically moves on this line, so it goes from some initial moisture content omega-1 and a temperature T1 to a lower temperature T2, but a higher moisture content omega-2. Okay, and it tends to move along a constant enthalpy line or a constant wet bulb temperature line. And this process is very similar to the adiabatic saturation process that we discussed before. Okay, so this is the whole concept of evaporative cooling in a nutshell. Now, if you were to ask how does evaporative cooling works, and here we're basically making use of evaporative cooling, like the discussion that we are having here. It's basically the use of evaporative cooling to cool down air. All right. Although we said we are also cooling down water, but here the key part is the air. That's what we care about an air cooler, for example. And since we're able to cool down the air, this is something that can be used to replace the conventional air conditioning systems, right? Like the ones that work on vapor compression refrigeration. So if you just compare an air cooler or an evaporative cooler with the conventional ACs, you will see that evaporative coolers consume 75% less energy, right? So they make a lot of sense, especially in hot and dry climates where the relative humidity of the air that's exiting the air cooler is in the desired range, which is 30 to 50%. These coolers make a lot more sense, and it's pretty obvious why they would make sense, right? Here you don't have any, you just have two simple moving parts. You have this fan which does not consume much energy, and then you have a pump for pumping water. That's all essentially what it is around a simple frame. So this is there is a very good example on this air cooling aspect of it, and the textbook is 12.13. Please go through it to understand how this is happening. We're going to look at one more application of evaporative cooling and solve a problem based on that. So which is sort of more involved. So I won't be looking through this for now. Now, if you have any questions, please let me know before we move ahead. Anything that's not so clear from our discussion?
Clear, Doctor.
Okay. All right, now let's talk about the other application, which is in cooling towers. Now, we have dealt a lot with power plants, and we know that we need to sort of reject heat in the condenser for a power plant, right? Now, in addition to power plants, there are also in also air conditioning systems, you need to reject heat, and some other industries where a lot of heat needs to be rejected exist. So essentially, there are, I would say, three major applications where you need to reject heat for sure, right? And this rejection can occur in the heat rejection can occur in several ways. The easiest probably option, if you're close to a water body, is rejecting the heat to a nearby lake or a river. Essentially, when I say rejecting heat to a nearby lake or a river, is that you dump this hot water into the river and take the cold water from the river as an input, right? So just using the lake or the river as a sink. This can certainly work in a lot of cases, but sometimes it's not feasible. Either because the cooling water supply that you have in a lake or a river is, I mean, it's rather small. I mean, you have a small artificial pond which is not large enough to, provide you the cooling that's desired, or maybe the thermal pollution that you're causing in those bodies is a concern. Maybe the temperature of the water that you're sending in is too high, and that's not, that can damage the environment of the lakes or the rivers. So you're not allowed to do that. So in such cases, or basically in cases where you don't have access to a lake or a river, then you got to think about another way of rejecting heat, right? We have to sort of reject heat, and we typically want to reject heat to a sink. So if it's not the lake, then we sort of reject the heat to the atmosphere. And we do so by using cooling water as our transport medium, or basically water as a transport medium for heat rejection, right? So we use we send in water in the condenser that gets hot, and because of heat rejection from our working fluid, whatever the working fluid is, and then you send this hot water uh, either to a cooling tower or to maybe some sort of uh, a heat rejection system where you reject heat from the water. Okay, so there are several ways of cooling water, of course. One of the most commonly used is what's called as a cooling tower. So let's have a look at the schematic to show you how a cooling tower looks like. This is a schematic for an induced draft cooling tower, and here we say induced draft simply because we have a fan at the top to direct the airflow. Okay, now the way this cooling tower typically is designed is that you have the warm water that you want to cool down, right? You send it at the top at a certain temperature with a certain mass flow rate, and then sort of sprayed as water droplets. Okay, so you see water droplets falling down from the top, and then we have this atmospheric air, uh, usually at a slightly lower temperature. So T3 is typically lower than T1, and usually at a slightly lower temperature, being sent in at a location which is below the water inlet. Okay, so you send it from the bottom, and then you have a fan at the top to direct the airflow. So you're trying to pull in the air at the top. So basically, you create a counterflow. You create mixing of you create a mixing region for air and warm water to interact, and the water is coming down, the air is going up. Okay, and when they interact, certain amount of evaporation does happen, and that is where the cooling is effectively achieved. So you have some amount of water that remains as a liquid at the bottom, and because of the evaporation, you need to add uh, some small quantities of water to make up for it, because the water that we send at the end would be equal to the water that comes in at the inlet. Okay, so again, let's have a look at this. We said the water that's coming in as liquid droplets is interacting with the air. Okay, and evaporation does occur, and because some part of this liquid droplets, some part of the water that we sent in is getting evaporated. Typically, less than 2% of the liquid water gets evaporated. So because of the evaporation of that, the air that we had sent here gets cooled, as well as critically the water that we had sent at the top, it also cools down. Okay, and the reason it cools down is because it needs to provide the enthalpy for the part that converted from liquid to vapor, right? So there's some amount which converted from liquid to vapor. To provide for that enthalpy to go from HF to Hg, the enthalpy difference needs to come from uh, the water that remains as a liquid, as well as from the air. Now, the we have achieved one goal of we have achieved the main goal of setting up a cooling tower, which is that we have been able to reduce the temperature of the water we sent in. So we have having the water that's returning at a lower temperature than the inlet temperature, which is excellent. Now, since during this evaporative cooling process, we lost some amount of water to evaporation, or in the sense that it's been taken within the air. The air has taken that the humidity level of the air has increased, and the air has taken that amount of water. So we need to compensate for that, because we need to send back the same amount of same mass flow rate as what came in. So that's where we add up the makeup water, as we just discussed. So this is the main part which is happening. Although when we look at from the aspect of the air, well, of course, what's going to happen is that as air goes up due to evaporation, it's going more amount of water is going to get converted to vapor. So the water vapor content within the air is going to increase, or the humidity ratio of air is going to increase, right? And therefore, at the exit, one thing that we know for sure is that the humidity ratio at state 4 or the exit is going to be greater than the humidity ratio at the inlet. Okay, and this simply happens because of evaporative cooling, because the fact that water is getting evaporated. So we said we need to add makeup water to compensate for the evaporation, and therefore the amount of makeup water that you need to add is basically equivalent to the amount of water that got evaporated. All right, so that's all it is here. We're going to talk about some more types of, let's say, cooling towers or options available to provide the cooling effect, and then solve a problem based on this. If you have any questions here, please go ahead and let me know.
Doctor, I have a question.
Sure, go ahead.
Yes, please. The temperature will decrease because we have sprays at stage number 2, or what's the main reason that will cause a decrease in the temperature?
Okay, excellent. So we are actually spraying the liquid water. We are spraying the water here just to increase the interaction between the water and the air. Okay, so the air is going up, the water is coming down. We want the surface area of interaction to increase. We want it to interact as much as possible. Now, the key reason for the temperature of the water to decrease is because some part of the liquid water, right? Some part of the liquid water has to will get evaporated as it comes in contact with the air. Now, when we say it's getting evaporated, so basically liquid water is converting to vapor. So the enthalpy of this, let's say 2%, right? of the initial mass flow rate needs to go from HF to Hg, right? So this increase in enthalpy, it needs to come from somewhere, and basically it comes from both the water that remains, the 98% of the water that continues to remain as a liquid, as well as from the air that goes up. So, I mean, the way it comes from this 98% water is that its enthalpy goes down, right? So, it's going to remain at the same pressure, but the enthalpy is not going to be equivalent to the enthalpy of saturated liquid at that pressure. It's going to go slightly down, or in other words, the temperature is also going to go down, simply because that's how it pays up for this extra increase in enthalpy of the part of the water that wants to become a vapor. Is that clear? Do you want more
Yes, clear,
clarification?
Doctor. No,
Okay.
clear, thank you.
All right. Any other question? I mean, the key part here is evaporation, right? Evaporation is what is evaporation requires some heat input. Evaporation requires an increase in enthalpy, and for that to happen, the enthalpy needs to decrease for the rest of the components, right? It's essentially the entire system is in balance. So if you're increasing the enthalpy of something, then the enthalpy of others need to decrease, and that essentially is happening. The enthalpy of liquid water is decreasing, the enthalpy of air is decreasing, and that's why we are having a reduction in temperature of the water that we send in, right? That's how the water is getting cooled. That's the main part. Okay, so this is what we showed as an induced draft cooling tower, where I mean the airflow is happening because we have a fan at the top, and we are sort of ensuring the air is moving in that particular direction. Now there are also what's called as a natural draft cooling tower, which looks like a chimney, like the one shown here. This is a schematic picture of a natural draft cooling tower. So the way this works is that we don't have a fan at the top. It's just the shape and the fact that the moist air which is inside, right, has um, is lighter than the air outside, right? So outside air is heavier. So just because of this difference, we have the outside air entering from the bottom and pushing and moving through the top as it gets more and more moist. And so this airflow is basically caused because of the difference in in the density or the mass of the moist air as compared to the outside air, which contains less moisture, and also because of the way this is shaped, right? So here you don't need a fan, but of course the shape and the way it's designed ensures that you have continuous airflow, and essentially the same process is done. Now, apart from this,
Doctor,
yes, go ahead.
how can they ensure that the density of the moist will be lower than the density of the outside air?
Excellent question. So the thing is, when you're looking at outside air, okay, uh, it the assumption is that it has less moisture, okay. So now, why do we care about moisture content? Well, the molar mass for water is 18, right? 18 grams per kilomole, or kilograms per kilomole. Now, for the other components of air, the other main components of air, which are oxygen and nitrogen, their masses are 28 kilogram per kilomole or 32 kilogram per kilomole. Okay, so if you're adding more moisture into the air, then basically what you're doing is you're sort of reducing the mass or the density of the air as a whole by adding a component which is lighter. So this is basically, I mean, the difference is going to be rather small. I'm not saying the difference in the densities is very large. It's small, but it comes from the fact that we're adding a lighter component, and the more is the lighter component within the mixture, then of course the as a whole the mixture becomes lighter. And this is simply because water is lighter than the other major components of the air. Does that answer your question?
Yes, thank you, Doctor.
Yeah. So yeah, the differences are pretty small. That's why we need the shape as well. And it sorts of ends up directing the airflow, where you see these holes at the bottom where the outside air comes in. So this is one option. There are also other options. You could make use of, let's say, a spray pond or a cooling pond, where you're doing essentially the same thing. You're sort of spraying the water, and the water is going to get cooled by due to evaporation. It's just that in a spray pond, you're going to need a lot more area. So this is a picture of a spray pond right here. So you have like sprays that you can see around, and the water that we're going to take is this water at the bottom, which is liquid, right? And this is going to be cooler than the water that we are spraying through those tubes here. And of course, it's another way, but it's in terms of the area, it's not a very efficient way, because it's going to require about 50 times more area than a cooling tower for achieving the same, let's say, the cooling need, right? And the other option is also a cooling pond, which is essentially a huge artificial lake where you just dump hot water and take in cold water. Of course, the water content should be so high that, when you're adding hot water, it should not change the temperature so much of the water that's remaining. So again, this is going to be more space inefficient. It requires a lot more area than even a spray pond. So of course, so when you look at all these options, cooling towers are the most space efficient option of meeting the cooling needs, and therefore they're extremely popular.